Let's have a go at the next question. So here we have a question dealing with gases. Gas of mass 0.23 gram is trapped in a cylinder by a piston. So we have the mass presented in grams as m is equal to 0.23 gram. The gas is at an atmospheric pressure, which means the initial pressure P1 of the gas is 1 into 10 power 5 Pascal. Figure 4.1 shows the piston held in position by a catch. Here, the presence of a catch implies that the piston is not allowed to move. In other words, the gas molecules are trapped within this closed container. The volume of the trapped gas, the initial volume V1, is 1.9 into 10 power minus 4 meter cube. An electric heater is used to increase the temperature by 550 degrees Celsius. Here 550 degrees Celsius is neither the initial temperature nor the final. It is just the difference in temperature, which is 550 degrees Celsius. They have also given the specific heat capacity in part A. The specific heat capacity C is 0.72 joule per gram per degree Celsius. Usually, I would have asked you to convert mass, which is in grams to kilograms. But since here, the specific heat capacity has the unit gram inside it, there is no need to convert mass into kilogram. We can and we should substitute mass in grams. Moving ahead, we need to calculate the energy required for this temperature change. The energy required, capital Q, is given by the expression Q is equal to M into C into delta T. This is the expression involving specific heat capacity discussed in section 2. Here we have the substitutions of mass is 0.23 grams kept in grams. C is 0.72 joule per gram per degree Celsius. And the change in temperature is 550 degree Celsius. When simplified as such, we get the value of energy to be simplified and approximated using significant figures as 91 joules. Moving on, we have the power of the heater, which heats up the gas molecules as 2.4 watt. We know that power is the rate at which energy is consumed, or power is energy by time. If we need to calculate how long it takes for the heater to supply the energy calculated in subsection 1 of part A, we just have to make time the subject of the equation, as time T is equal to energy by power. Substituting energy from subsection 1 as 91 joules and power as 2.4 watt, you get the time to be approximated at 38 seconds. Moving on. In practice, it takes much longer to increase the temperature of the gas by the same value, which is 550 degrees Celsius using the heater. Suggest one reason for this. Here we understand that the power supplied by the heater is going to remain a constant value of 2.4 watt. If power is going to be a constant, the relationship between energy and time is such that energy is written as power into time. And since again, power is a constant, energy is directly proportional to time. So here, when they say that it takes a longer time, they are indirectly trying to imply that the energy consumed is also more. The energy consumed is or could be more. The energy consumed is more, could be one of the following or all of the following reasons. The first could be that a part of the energy is absorbed by the piston. A part of the energy could also be absorbed or dissipated to the surroundings. Moving on, part B asks us, when the temperature of the gas is increased by 550 degrees Celsius, pressure is 2.9 into 10 power 5 pascals. We understand that the pressure P2 is equal to 2.9 into 10 to the power of 5 Pascal, which means the value of the pressure has increased by a factor of 2.9. The catch is then released, allowing the piston to move. As the piston moves, the temperature of the gas remains a constant. State and explain what happens to the piston. So we understand that as the piston is allowed to move, the pressure increases. And since the pressure increases, the piston, which is now free to move, moves towards the right or moves to the right. Moves to the right. Now, the piston moving to the right is a consequence of the increase in pressure. And pressure is just the force applied by the gas molecules onto the walls of the container and that of the piston. Now, the last part asks us to determine the volume of the gas when the piston stops moving. So we know that pressure P into volume V is a constant, or another way of writing this is pressure P2 into volume V2 is equal to pressure P1 into volume V1. Since we need to find V2, we make V2 the subject of the equation as V2 is equal to pressure P1 into volume V1 divided by P2. We have the substitutions as V2 is equal to P1, which is 2.9 into 10 to the power of 5 into 1.9 into 10 to the power of minus 4 divided by 1 into 10 to the power of 5. This gives us the value of V2 approximated to 5.5 into 10 to the power of minus 4 meter cube. This is the solution that is explained in the mark scheme. Although I believe there is a mistake here. Here the volume V2 is found out as P1 into V1 over P2, whereas the values of P1 and P2 are exchanged. This is the value of P2, whereas this is the value of P1, which gives us the new value or the correct value of V2 to be 0.66 into 10 to the power of minus 4 meter cube. This is the correct value, which has not been provided in the mark scheme for the particular question. And this makes sense because since temperature is a constant, pressure P is inversely proportional to volume, which tells us that when pressure increases, the corresponding value of volume should decrease. And correspondingly, the volume decreases from 1.9 into 10 power minus 4 meter cube to 0.66 into 10 power minus 4 meter cube, which is by a factor of 2.9, which is the same factor by which pressure has increased.